everyone. I would like to thank the organizers very much for inviting me to give this talk. And just start out as is traditional by lowering your expectations a little bit. As you can see, this will be a low-tech presentation for long and complicated personal reasons, but I apologize in advance for the fact that I'm not really taking full advantage of the medium here. So my goal in this talk is to answer the following question. How do we think geometrically about uncountable groups? And the motivation for this is probably pretty clear. I like to think of myself as a geometric group theorist. I'm trying to study big mapping class groups. Big mapping class groups are uncountable. But I will say they do have a little bit of extra structure to them, which will turn out to be pretty crucial, which is they have a natural topology, which they inherit from the group of homeomorphisms of which they're a quotient. So to answer this question, I want to first spend probably most of this video talking about how we traditionally think geometrically about finitely generated groups, and then we'll see how we can generalize that. I should say at the outset, these are not my ideas. This is background and motivation for my ideas, which are in the second video, but I also think this stuff is really cool on its own, and I like to talk about it, as you can see. So suppose G is a finitely generated group. So we have a finite set S which generates G, and G acts on X, which is a metric space. And since we're acting on a metric space, we're assuming we act by isometries. Now here's a very simple fact. For any base point we pick in the metric space, there is some constant k such that for all elements of the group, the distance in the metric space from the base point to the translate of the base point is bounded above by k times the word length of G with respect to this finite generating set. And the proof is basically just let k be the maximum distance that any generator takes to point x0. Okay, this isn't quite a proof, but it's close to one. Right? If our finitely generated group acts on a metric space X, then just by virtue of being finitely generated, there's this sort of natural Lipschitz condition that you can't move a point any farther than some universal constant times the length of the word you're moving it by. And this is sort of the beginning of a lot of the point of geometric group theory, right? And this is true of any action, right? And I would say, in some sense, this is what justifies word lengths being the main geometric way in a lot of cases that we think about groups, is trying to, you know, describe things in terms of word lengths or estimate word lengths, so on and so forth. It's because of this fact deep down inside. But also, if we add a little bit more requirements to this action of G, then we can say something stronger than this, right? So currently, G is just any action on X by isometries. But in particular, it could be something like the trivial action, right? So we're never going to get a lower bound in this general case. So in order to get a lower bound, what do we have to do? Well, we have to assume that G acts with a little bit of extra geometric regularity. So suppose G acts on X geometrically. And what I mean by geometrically here, this is not quite the way it's usually stated, but it's equivalent up to some assumptions that I'm going to call reasonable. G acts on X geometrically, and by that I mean for any diameter B, the set and any base point, the set of elements that move the ball, that move the point x0 less than a distance b, right? Or equivalently, you could think like the set of things that map the ball of radius b onto itself, or maybe b over 2 or whatever. If this guy is also finite, okay, then we get a lower bound in addition to our old upper bound, right? So we still have the distance from x0 to gx0. So put in my quantifiers here. For all x0, there exists k, and we're also going to need c now, such that for all g and g, we have our upper bound from before, possibly with a different k, but now we also have a lower bound. Excuse me. Now we also have a lower bound, which we can put here. And the reason we need this minus c is that this guy could be 0, but only if the word length is small, because by this fact, there's only finitely many things that do that. And if we just decorate this with a little bit of extra stuff, okay, so let's add plus c here. It's not actually needed if you look at what makes this true, but it makes it more symmetrical, which will make it an equivalence relation. And I also say, and this action is co-bounded, right? By which I mean that if you quotient by the action, you get a finite diameter metric space. I don't know if this is standard terminology. I'm thinking of this as like co-compact, but for a metric space which might not be proper. Feel free to let me know if there's a better word for that. But if we're in this situation, right, then this stuff plus the co-boundedness means that G with the word metric and the metric space X are quasi-asymmetric, and this, of course, is the famous Schwarz-Milner lemma, which is the fundamental idea, arguably, of geometric group theory. So, there's two things, I guess, that I want you to notice as consequences of this guy. And again, I've done this relatively quickly under the assumption that you've probably seen some version of this before. But I guess what I want to claim is that this is not too hard a fact, right? I mean, it takes some ingenuity to realize that it's useful. But the statement kind of follows from the definitions, right? It's not too hard to figure out what K and C have to be once you know this information. So two things you can get from this, right? One is if we switch out for a different finite generating set, then we still have this quasi-asymmetry, right? In particular, X could be G with a different generating set, just acting by left multiplication. And so this means that all the different choices of generating set for G give you quasi-asymmetric metrics on G, which is a desirable property if we want to study groups geometrically. We need some equivalence relation so that a single group won't have different geometry depending what angle we look at it from. The second thing I want you to notice is that finite is used twice in this, right? We're assuming the generating set is finite, and we're assuming this guy is always finite. And in the proofs, right, if you think about how this goes, we're not actually using finiteness per se. We're just using the fact that a word of finite length can't move you very far in the action. So the key idea is we're going to generalize this finiteness into something more broadly applicable. And of course, in the end, we will be able to wrap this around and connect it to big mapping class groups. Okay, so the idea will be that instead of finite, we're going to have a new thing, and you should think of this as being almost as good as finite. Okay, so here's a definition. It's due to Christian Rosendal, or at least this use of it is due to Christian Rosendal. Given a topological group G, okay, and if you don't want to think of G as a topological group, just give it the discrete topology, say, and then everything is continuous, so that's fine. Given a topological group G, a subset A of G is coarsely bounded So we want this coarsely bounded thing, right, to have the useful geometric properties of finiteness. And what is that, the useful geometric property of finiteness? Well, it boils down to this. Whenever G acts on X, and here this action is assumed to be continuous and by isometries, right? Whenever your group G acts on a metric space continuously by isometries, for all x0 and x, the set of translates of x0 under elements of the set A is bounded. Okay, and it's worth mulling over this definition for a minute because it's actually a really hard thing to achieve, right? In particular, right, for A to be a coarsely bounded subset of G, this statement has to apply for everything that G could act on, not just in one case, right? You can always find some action where it's small, but this is somehow a property that by the topological properties of the group, any action will produce this any action will produce this boundedness. Obviously, you could scale it, right? So it's not universally bounded, but for any particular setup, this guy's always going to be bounded, right? So I just want to So the examples you should have in your head to compare this to stuff you know are if A is finite, then this is certainly true. Or if A is compact, this is true. Okay, and the best non-example is if A is unbounded with respect to some metric on G. Right, G acts on itself by left multiplication. So if A itself is unbounded for some, nice compatible metric on G, this isn't going to work. Okay, and with this setup, and this definition of coarse boundedness, we now have a really nice statement, which is kind of a natural extension of the Schwarz-Milner lemma. So if G is generated by S, and S is coarsely bounded, and G acts on X such that for every B, the set of G such that the distance for every B and for every x0, distance from x0 to gx0, if this thing is also always coarsely bounded, right? And this is the second use of finite in the original Schwarz-Milner lemma. Then for every x0 and x, there exist k and c such that for every G in G, the distance from x0 to gx0 is bounded above and below in the way that we're familiar with. And this is due to Rosendal. Obviously following Schwartz and Milner. Right, and what's so nice about this is once you have the right definition for coarsely bounded, the standard proofs of the Schwartz-Milner lemma just follow. Because the definition of coarsely bounded really captures what we cared about for finiteness. Okay, so given that definition of coarsely bounded, and it can be a lot to swallow. Thankfully, it's a recorded lecture, so you can go back and ponder it. I hope those examples are helpful. But once you have that definition, now we have a much larger class of groups, right? Not just the finitely generated or even the compactly generated groups, but the groups with coarsely bounded generating sets, which sometimes get called CB generated. Now, for all of those groups, we can do this geometric group theory thing and talk about the quasi-isometry class of the groups. So I have a couple minutes left. And finally, I will just note that recently, Katie Mann and Kazarafi, up to a technical condition, classified all infinite type surfaces whose mapping class group admits a coarsely bounded generating set. And I will link this paper in the video description, as well as Rosendal's book on coarsely bounded stuff, which gets into a lot more, obviously, than what I've said here. And so the takeaway is we now have a large set of big mapping class groups, definitely not all of them. There's uncountably many where this is possible and uncountably many where it's not possible. But we have a big interesting class of them, and we can ask, okay, these have a well-defined geometry up to quasi-isometry, what the hell is it, right? So we can now ask, what is the coarse geometry of these groups? And my second video will be precisely an answer to this question. And all right, I did that within time, so thank you again to the organizers, and I will see you in the next video.